Well, hello, and welcome back to Old School Coding, where I'm using a computer language of the 1990s to build a simulation of a computer system that might have existed in the 1990s. And we're going to be using techniques of the 1990s. So, yeah, nothing more modern. And if I seem to be using more modern techniques, just think for a moment, where did those techniques come from? And that camera is pointed wrong. There we go. That is slightly better. Anyway, so at the end of the last session, I was grousing a bit about all of the test programs I had that basically the test code in C would do the same thing. It would load up a hex file and go run it and evaluate the results. And I had several of those. And they all did all the steps internally. I thought, let's unify that. So I did. So that began a afternoon of refactoring. So first off, we ended up building test. Let's get into the right directory here. This thing, i8080 ASM test. This encapsulates all of the logic for all of the tests that were loading up a hex file from assembly code source. We had the assembly code source, it got turned into a hex file. It then gets turned over to i8080 ASM, which does basically all of the boilerplate around running the hex file that allows my test to collect the outputs. So as part of generalizing this, I thought, let's make it more generally applicable. So I beefed it up a bit. But the core is really the same. During post, we are going to continually run the clock one step at a time until we get the test done signal. And I need to think about to do provide a timeout here. Because it's possible that a fault in the simulation could cause the test to never encounter a instruction that terminates the test. Now we communicate results from the test back to the C code, back to the simulator, using 3 opcodes. We have changed those over to use 3 of the illegal instructions. Bada bump. And we set them during the test and we restore them at the end. Also, to make the plots more approachable, I have set tri-state to all of the things we might be plotting. We can add more adder Z and data Z things up there. Bist is just like post, except that it also calls this plot sigs. So we run the same test programs for the power on self test, which runs every time we run the simulation, as we do for the built-in self-test. Now, a test could say, well, run my program only for Bist. So we don't have to, but we're providing the same logic here. The difference is that if you're running during Bist, we collect the trace information from the CPU and plot it out. Same thing, intercepts. We load the hex file into the ROM. The 0 here says this ROM is starting at 0, so load the hex file as if. We may adjust things a bit at some point in the future if we want to run out of a ROM mapped into high memory, but I think it's still safe to say load the ROM at 0 and we'll just make sure the hex file does the right thing with the address range for the ROM. Do need to remember that though. We may have to call load twice, once for the ROM there and once for ROM high. We'll get into that at some point in the future. The instructions that we intercept, this is just like the ones we used over and over again in all the other cases. If we have a test fail, we're going to print information about this test failure, including PC -1. Remember, PC has been incremented before we get to this state, because this is being called during T-state number 4 of the machine cycle. So PC's already been incremented, so we decrement PC. Well, we print PC -1, so we get the actual address of the illegal instruction that we used to trap here. We got test done and test page. So that was the first one. The second thing was I recognized that I had a lot of little teeny bits of boilerplate spread throughout my code. If you look on the right, you'll see I'm using a bunch of macros now. So for instance, lower weight over here on the right, that was edge underscore low of CPU arrow weight. Or this guy, adder underscore 2 of CPU arrow SP, comma, CPU arrow data, arrow value. And it was that same thing, same pattern over and over and over again. I thought, well, let's macroize that. That means I can look at it more clearly here. It also means that at some point in the future, perhaps these do something slightly different. Maybe I want to change all of my calls that lower a signal to do something slightly different from what it's doing. So now we capture all of those APIs over here on the left. Now we're assuming that for these particular macros, which are at i8080 impl.h, these are primarily operating on a CPU structure to which the CPU variable points. Think of CPU as this in an object-oriented language. Or self, if that's what your favorite language uses. So, a bunch of things here. Val, inc, dec, constructing a register pair, so fetch 2 registers, make them into a pair, or take 2 values and pack it into a word value as if it was a register pair. Lower and raise a signal, set a signal to a value, set an adder to a value, tri-state data, and tri-state address. Now, if we want to really grind on this, make the simulation faster, dtry and atry may simply expand to nothing. So we can get rid of all of these things that do the extra step to tri-state guys, all in one place. So what I've got on the right is the implementation of the LXI instruction, which is, it's got 2 bytes of immediate data, which it loads into a register. And I'm going to swing into what I want to implement, which is load and store. So let's go back to, actually, we're here looking at impl. I might as well put LDST. So wherever I have a stack, I'm going to duplicate the line. I'm going to change the word stack to LDST. That's got that. Oh, as part of refactoring, I also broke the opcodes out into their own header file, and I broke the list of phases out in their own header file and the status, because not everybody needs to see all of that, and actually it's easier for me to maintain if I have them in separate files. So I can go right to the status file. I can say, okay, those are the bits. And I can watch the status file for changes to see, is anybody changing anything that deals with the status file? So this immense programming team, which is comprised me, myself, and I, well, past, present, and future, so there's 9 people on the team. Right, and we need to communicate between all of them. Well, really, it's, from the past to the future, but you get what I'm saying. By keeping these separate, it means that I can more quickly narrow down what changed and what maybe I changed that I shouldn't have, or where I should change something. But that does mean we need to go to test, and we need to apply our macro. Everywhere we have stack, we need to add LDST. Okay. Test, i80 test.c, do the same thing here. And this guy is a little bit of extra work since I need to also fix this reset for testing thing. This is looking more and more like it's almost redirections just to a function pointer. I have eliminated the jump and IO test file in favor of simply having it execute those. I may return to that if I decide that this is better done as a list of pointers that I reset for testing and call through the pointer on. We'll see about that. We've already done that one, and that's it for that guy. So now if we look at our compilation, we have a bunch of undefined references. Well, that's okay. Just by chance, I happen to be doing the test first this time. This is not important. I think I want to do the LDST tests. I think I want to do them. No, okay, I would not be able to do them purely in an ASM file because we still haven't written the part of the simulation that turns off shadow. So I can read from ROM, I can write to RAM. I can't read back from RAM, so my test programs cannot read from RAM. So I need to do kind of like, not LXI, what is one that, oh, well, stack test, for instance. So we're going to start with stack test. LDST test.c. File off the symbols, LDST test the load and store instructions. So get set RAM to a known non-matching pattern. Check that appropriate bytes have changed. Like that. Test on it, run it, done, test on it, run it with plots, done. And we are going to be working on this guy. RAM area test size, I'm going to do a whole kilobyte of this. Well, no. I mean, how many things am I going to load and store? Really? And this guy, there. Actually, I'm just going to comment these out for now. And let's not do it that way. Beginning of line, 2 slashes, and done. So RAM is being used. Actually, let's leave one of these in. So probably what I'm going to be doing is loading and storing from some constant area there at 128-ish. So LDST test doesn't exist yet. I really am writing the test first this time, aren't I? So now I need to put in a bunch of these guys. And we will fill this in as I do the implementation. That gives us something that executes. And that will make it so the test passes. Haha, will it? Will it really? So it's 5A is the value that's being stuffed into RAM. Okay. So now all we need to do is start working on the implementation and then fill in the test program with the things we're implementing so far. So I8080 LDST.c. And maybe starting with this guy was the wrong thing because we do not have a huge swath of load and store instructions. I missed a to-do. In fact, I don't know. Well, we will find out as we do things. We definitely are not loading and storing the stack pointer. Says he definitely saying something that definitely might be wrong. So LDST init, let's go hook that up. So where we have stack, I need to go in and say LDST. Here I'm going to verify we're getting here. Print top. So we are getting into LDST init several times. So this is each time we do a power on self-test or built-in self-test of the CPU, it's going to be calling into LDST init. And it is, in fact, doing that, so we can safely get rid of this. Now, let's take a look at our PDF to decide what load and store instructions we want to start with. Yay, PDF on screen. So we have a number of these things that count as loads. LXI we've already done, that's load immediate, so the immediate goes into the register. We want to do things that do memory. We've got load accumulator, which has 2 immediate bytes that define an address, followed by loading the data. We have store accumulator, 2 immediate store the address, and we store the data. Okay, those are solid. LHLD and SHLD are similar. We have an immediate address, followed by writing the low and high bytes of the thing, or reading the low and high bytes of the thing using WZ. And then we have these LDAX and STAX instructions, which are slightly simpler, okay? This says that we are going to use the BC or DE register as the address and move from its thing into the canvas. So this is actually more like a move M, A, but using something other than HL. Okay, LDAX and STAX. Oh, Exchange. Do I have Exchange? Exchange is like a trivial function. Did I do Exchange? Because that's like a move-like instruction. Hold on. Log, unimp. I don't see Exchange on here. Doc fig forth. LST source. Okay, so I have done Exchange. Good. Okay. Sorry about that. I can't always remember all the things that I have done, which is why I have things like my list of unimplemented instructions. Otherwise, I would do things like I would forget, oh, there's one, XTHL. And I did that all behind this panel. So we have not implemented the XTHL instruction, which is the troublesome one. Anyway, we're still looking for loads and stores. So we've got LDA, STA, LHLD, SHLD, LDAX, STAX. And we go down through here. I'm just going to really quick look at things that have, this is push and pop. Okay, XTHL. This is really a stack operation, and I avoided doing it during my stack work, and I'm going to avoid doing it now. This is going to come in last because one very simple thing. How often do you find a errata in a 50-year-old document. Now, I will get this in detail when I start implementing it, but you'll notice XTHL says we are storing, well, we're fetching 2 bytes of data. So SP out, increment SP, data from SP goes into Z. SP out again, data from the second byte goes into W. Here, we are writing H and L to the same address. So the errata is we need to decrement SP here in M3 and increment it here in M4 so that these 2 addresses that come out are the proper addresses for H and L. Alternately, it's not clear to me why the engineers didn't say we're going to SP out to read the data, and then instead of increment by 1, do an SP out and an SP out to read the data, and then you increment the SP, and then you do it a write and a read. So I would have done byte, I think, looking at this. It depends on the cost. If this is easier to decode, then all we need to do is toss in something here to either retain the prior SP value or decrement and increment. Now, our increment decrement register, IDAL, does provide us with this ability to store back the incremented or decremented value during the T2 cycle. So this is what I think is happening here. Anyway, so we're going to defer XTHL until a cleanup episode later on. And we're going to be looking at that in detail. That's going to be an implementation and a test on its own. We're going to examine the signals and so on. So LDST, we're looking at these instructions right here. And I think what I'm going to do is I'll do the LDAX and STAX first. Okay, this is footnote 4, which says only register pairs BC and DE are specified. So this is two register pairs involved in LDAX, STAX. And it simply sends the register pair out and gets the data back. So it's like the move from M. We'll do that first. Move the PDF off to the side here and turn it off like that. So we need to declare the function. So first of all, static if, this is going to be a macro because guess what? We have LDAX for 2 different register pairs. And okay. And we are going to be defining them. Now, there's a possibility that we need more than one macro state function. Let's take a look at the PDF again. Focusing on LDAX and STAX, the T4 is going to be just this one function, which does nothing and arranges for the M2 cycle. During the M2 cycle, this moves from data to A or A to data. So this will look very much like the move instruction for A. But that does mean that we do need to have that set up. Let's take a look at the move instruction. PDF off. Okay, so move M. These are the RD variants. Okay, so that would be move M. What I want to do is change that to be LDAX and STAX. So for instance, we would start with there. And these are going to change. Let me put the implementation down at the bottom. So as I do these global edits, they will get the right thing. So LDAX T4RD, we have T4, we have T1 read, T2 read, TW read, and then we're going to have our macro function, which looks a lot like this. And in fact, all of these guys are macros because I am not going to waste my time So let's do the naming. So we have LDAX M1T4 RHRL. We have name LDAX of M2T1. Actually, we can just edit these. Oh, come on. M2T1 becomes M2T2. M2T3. T3 becomes TW. And as usual for my pattern, I am spending instruction space to save memory indirections. Okay, so there are the, oh, and I need T3 in there as well. So T4 for the decode, T1 to start the machine cycle to do, T2 to end the sync pulse and move the data, start the data moving, T wait as necessary, and T3 to finish up. And now if I look at the compiler output, we see we've got a whole bunch of things that are badly done. Type defaults to int in declaration of def and LDAX empty. M2T1, M2T2, M2TW, T4, 1, 2, wait, 3, 1, 2, wait, 3. Okay, so we need to do one more thing. I'm going to need to take a look at the make pre I 8080 underscore LDST.E. So this claims that we are attempting to type defaults to int in def and LDAX M1T1. So after expansion of macros, this is what we're getting. Because this is M1 and it's supposed to be M2. There we go. Going to continue to update that .e file as we go because there's likely going to be other weirdnesses in macros. But this says now that we have LDAX M2T1 RD is undefined. Right, because all of these guys now have to change. So LDAX M2T1 of the proper thing. So these guys, LDAX, these need to be macroized based on the register pair. Get back into LXI here so we can look at the definitions. And again, I have not consistently gone through to change this. We need a decal and we need an impl. So what this ends up looking like is T4BC, BC. Now, there's only two of them. So I'm just going to do it straight up like that. I'm not going to use macros because there's only two. And macroizing it is possibly considerably more complicated. So I8080 LDAX underscore, these need to be state LDAX. So I80 underscore state underscore LDAX underscore. Okay, so state underscore LDAX. I8080 state LDAX M1T4 BC. Right. I think I'm going to put a underscore before the register pair. So M1T4BC, M2T1BC, 2T1BC, hands it off to M2T2BC, and M2T2. Screw it, I'll macroize it. Okay, so the declaration is going to look like void name. Well, let's use a keyboard macro to write the program macro. Decl underscore that. Void name underscore that of RHRL I8080 CPU int phase. And then we have the impl on the next line. Which is going to start off with static decl underscore that RHRL and backslash, and the next line we are just going to say abort like that. In fact, let's just put that on one line. So we're going to start off with the impls all just being abort. And I will know to go grab the implementation from over here as case comes to case. So, state LDAX M1T4BC declared static but never defined. That's because we need to actually do it. Okay. The other thing I want to do is kind of group these together so that I can read them a little more readily. I think the easiest way for me to do that is to keep the define decl first to do add comments here. So once I've done that, now I want to do the same thing for impl. Pound define impl LDAX of B. So for this to work, these guys need to end in a static declaration. Okay, we'll need the name of the macro in my cut buffer. Define impl underscore. We're going to grab this. We're going to go out to here. Actually, let's do it on the end. Define like that. And I can put the escape new lines in momentarily. Okay, I8080 state LDAX M4T define static but never Okay, we have not defined a board. Unused parameters, yay! So let's start filling in these impls. So where we see abort, I'm going to put a backslash there and set this up. We're going to find the close thingy, and we're going to do that. We're going to place these at column 72. Okay, next step is to put the voids in. So, the warning, state LDAX M2T3DE, defined but not used, yada yada. These are all defined but not used, which means I have these getting defined properly. Each one needs to link to the next one, and then we need to pop the one in the top. And I think we can do that easily enough. Well, let's start by putting a switch statement into each one. With no content. Oh, let's put in this one. So all the places where we have void phase, I'm going to change to this. Should get the same set of errors. Yep. So wherever we have this guy, I am going to hop down to the next one. So static decal. And this guy is going to pick up, where did we do that over here? This is raise M1. We're going to also put in the lower the weight as long as we're thinking about it. And I can dump out the to-do impls because we are now actively doing something inside CPU in each one of them. And it's just the M1T4s that are not there yet. So now, CPU arrow M1T4 of op underscore LDAX BC is equal to okay. That hooks everything up. Now the instructions are currently doing absolutely nothing. Well, they will be stepping through those phases. So now we need to fill them in. So M1T4, we do nothing except dispatch to the proper thing. So it's opcode, decode. M1T2, this looks a lot like 2 bops. Or a lot like mauve of M. I believe the mauve instructions will use 2 bops. Is that correct? Move register definition, comma M. So I used this mauve T4RD. And that uses mauve T1, T2, M2T1, which does all of this. So we're going to start copying things in. Not sure why my indenter tried to do that, but fixed now. So a set ideal of, and it's going to be RH and RL. So we're going to take the high-low registers of the register pair. We're going to fetch the values, pack them into a 16-bit, toss them into IDAL, send it out to the address, and this is a memory read. And this needs to be here. If we're ready, we go to M1, M2T3, and if we're not ready, we go to M2T wait. And that's in the wrong one. There. M2T1 sets the stuff up and heads to T2. T2 is going to decide to go to wait or not. T wait has to decide whether to stay in wait or not. Back to T2. T2 read does these things during phi 2. So we lower sync, tri-state. Oh, there's the other thing I changed. Been talking about that we shouldn't be messing with data until we drop sync. So I did that globally as I was switching to macros. So we lower sync, then we tri-state data, and then we assert DB in. These all happen in the same tau. So at the same time for the simulation's sake, because it quantizes, but they are sequential operations. So if somebody is doing something on the descending edge of sync, they will still see the status word on the data bus, which I believe is required by the timing diagram. And by the time dbn is rising, we will have tri-stated the data bus, and we're ready to receive data. So M2TW, I'm going to copy that, including the comment. Do not use comment end of line inside macros, because it will comment to the end of the macro as the new lines are taken out. So we set the value to 0 and issue arrays. We do this in every wait state. Now, if it turns out we're executing enough wait states for this to be significant, I may extend the API for the edge to allow a re-raise. I don't believe this is going to be significant. We do need to raise the wait signal here. Okay, M2T3. Lower weight and red M1, we already had that. And now we want to capture the data. And that goes in the A register. So at this point, we can see that M2T3 doesn't use RH or RL, so this doesn't have to be duplicated for the two. And this guy doesn't have to be duplicated. So the last one, so it's just this M2T2 that needs to be duplicated. And I am taking a minor coffee fault. I will be right back. And there we have it. Coffee fault serviced. And while I was gone, we had the compile happen. I actually hit that before I left, but hitting it again doesn't hurt. So again, this all compiles. We're not executing it quite yet. But in theory, this means we should have LDAX done for those guys. So now I could go into my ASM stuff, and I could go here into the LDST test, and I could say LXI BC, comma, data, LDAX BC. What I'm going to do here is I'm going to put in a pattern 5.5 hex. Actually, let's do 1.1. Data for compare immediate with 1.1 hex and J and Z to pass 1 and test fail is a dB. And I believe that triggered a build. Yes, it did. So we got an abort. Oh. Looks like BC data, so we should load that into the data word. And LDAX BC. Oh, I know what's happening. Nope, we did call this. Let's put some stubs in. Set op %02x %02x h. Okay, and boom. So we did get into this. We did do the setups. And we're still getting into this abort here. In live coding. So here's where we are. Behind my head, you can see the one line of output we got, which confirms that we set the ops of 0A and 1A. If I go over here and we go into doc I8080, we can see 0A. Well, can't really see it. 0, 1, 2, 3, 4. 7, 8, 9A. 0A is here. Why do I have pound set there? LDAX. Let me make sure I have a documentation error here before I go correcting the documentation. Yes, LDAX and STAX take a register. Like that. Which means probably inside source. I have a thing that decodes instructions. Was that in test? Flags, impl, opcodes. Those are correct. So it's I-8080 instruction name. Yep. Which means gen opcodes has the wrong data coming in. And I'm just going to edit this by hand for now. So STAX, there we go. So our opcode decode is now correct. We're still down to where did we crash? So main frame 18. Main post, oops, down, goes to there. And the debugger is just going to choose whichever window it wants to put my stuff in. So LDST post calls ASM post of that, which calls into clock run 1. So there's our CPU state. Lordy, lordy. So PC value is 4. And let's see, no, LDST test. Here we go. So apparently I haven't done CPI yet. Yeah. Really? We define it there, and we use it there. And we never set it, which means this test program should never be succeeding. I don't use off CPI when I'm testing. Yeah, okay, so we do have it. So this says the instruction we're actually executing is 1, 0. Hmm, 10 decimal is 0x0a. So this is LDAX BC is not properly initialized somehow. Well, let's see. Are we getting to where I think we are? Edge high clock. Edge 2, subs run. Step run. Edge gen phi 1. So we are moving phi 1. We're rising, which calls into here. Optimized out impl LDAX BC, somewhere in here. So this implementation is calling abort somewhere. There we have it. Greg was an idiot. Let me pop that up in a decent window. I-8080 LDST. So, minor lesson learned. If the program is aborting, look for abort statements in your new code. Quit. Out of the debugger. Okay, so there we have it, and we've got our stubs being executed properly. So we are setting the ops. We are, yeah, of course, the line number here is where we instantiated it. So we are saying next is M2T1, next is M2T2, and wait. Oh, these are all on the same line, so of course it did that. So T1, T2, T-wait, T3, LDAX done. There we go. So in ASM test, a fail got hit. So I want to turn off the abort. Here, so that I can see my trace coming out. Hold on, I thought we went into fail for this abort. So assertion. Oh, that's just an assert. There we go. So now I can disable the abort within this test so we can get our good plots done. So expected value is 1, observed value is -1. Okay, that's good. And LDST state fini, the test is going to fail because the observed value wasn't set, and that's because my test isn't yet written. And we have another one here. Okay, so we'll have a few of those. The important thing is now that IMG should now have our LDST stuff. I'm going to wipe those out so I can be sure that they are being regenerated. So here's the first page, ASM LDST test. So we should have on the first plot LXI BC data. So BC gets 0008 here. And then we do our LDAX. So A should now get the 1, 1, and we're seeing it here. And we are doing a compare immediate. Let's look at this on the LST. It's much easier to work with. CPI is here. And my test is wrong. This is JNZ to pass. It should be JZ to pass. Okay. Accidentally, I did a good thing, which is write the test in such a way that it shows I can fail. And that's better. So now the test failures we have are because our test is not comparing the right thing. Can I say $+1 like that? Oh, dollar is the start of the JZ instructions. This needs to be skip over 4 bytes. So what we're going to do here is also do an STAX BC. Okay, so now we want to do the same thing. Actually, let's call this BC data and DE data. So that's working. What's wrong? There. So now we need to do STAX. So STAX just like LDAX, but no wait states. And I'm still not happy that I don't have wait states on my writes, because I think that must be wrong. So if we actually ran the instructions now, it would do an LDAX where I have STAXs. So STAX needs to do the other half of the cycle. So we get into source i8080 mov.c, and we look at the WR stuff. And we go over to the PDF and compare that. STAX still does nothing in T4. The difference is that in M2, we are going to be putting the accumulator onto the data bus rather than moving the data bus onto the accumulator. Let's move that over there for reference real quick. M2 T1, IDAL adder, this is status M right. And during T2, we lower sync and deset data val sub A. Okay, and then down here, after we lower, we do not do weight at all. We do lower WR underscore, and during here, we are going to raise why is it extending that for me? I do not know why the indenter is getting confused. Did I miss a semicolon somewhere? Nope. Raise M1, lower the right signal. We put the data in here. Lower sync, deset, next. Raise M1, lower right, raise right, tri-state the address. That should implement STAX as well. Warning, backslash new line separated by space. So apparently there was a blank after the backslash that I didn't see. So there we go. We are implemented, and now let's turn it on as LDST test. And there we have it. We are now staxing those back. So LDAX and STAX are done. Planning ahead for LDA STA. We're going to do that next. So LDA, STA take 2 bytes of data. So use 2 bops and 3 bops to gather them into Z and W. And then we are going to move data either from data to A or A to data. So let's do it. Now, really, we're just going to use 2 bops here, aren't we? Let's turn off the PDF so we can use that last column. This is CPU, arrow, state, 2 bops. Because LDA and STA are literally doing nothing until the T3 cycles. M2 T3 it becomes I8080 state, LDA, STA, M2 T3. They both do the same thing. They are going to be putting the opcode byte into the Z register. And then here on M3T3, this puts the opcode byte into the W register. And we need to declare those. Then we need M4, no, M3T3, LDA and STA, hold on. Yeah, okay, we have a machine cycle 4, which does a memory access with WZ to do either a read or write. So LDA underscore M4 T1, T2, T3, and STA. And how we get to that M2 T3, M3 T3, source. So 2 bops always uses M2 T3. We need to use I8080 3 bops to do the second byte, third byte of the opcode, which is the second byte of the thing. And that turns over code to us. We then need to turn over code to the proper guy on the other end, which means we need to decode here. D1, D2, D3. Get my line breaks in the right place. So the only difference between these two, M3T3s, 3, 4, 4, 3, 4, 4. The only difference between LDA and STA and M3T3 is who they turn control over to. That saves us from putting yet another table in the CPU. So we have a bunch of, oops, used but never defined, right. And then a whole bunch of declared but never defines. So now we need to build up all of this stuff at the bottom. Keyboard macro, void there. I-8080 CPU, int phase, switch phase. Okay, those should compile now and do nothing. Defined and not used, that's correct. Now we need to link each one to the next. We'll turn off the links for the exceptions, but find the null, find the void, get that word, go back to the null. Okay, so coming up from the bottom, 3 bops is not what we want to be looking at there. I-8080 mauve. Ret M1 int. There, so LDA doesn't chain into STA. Back up to the top here, and let's fill it in. So LDA, STA, M2, T3, which is we have prepared through 2 bops for it. So it is a T3. Go grab a T3 function here. Okay, typical T3. We might have had a wait state, so we need to lower wait. This is a load or a store. We have received data. We are not raising M1 because we're done. We, however, need to say dset the destination register. And the destination register for this is the Z register. So this guy now dives into, hold on, M2T3, yeah, that goes into, there should be a 3 bops in the CPU area, inc. Yep, 3 bops T1. Now 3 bops is going to go do its thing, and then it's going to come back into M3T3, where again we have to lower weight and capture the data, this time into the W register. So and this is, we have an LDA and we have an STA, which are separate. And they differ only in where they go. So this goes to LDA M4T1. Now, STAs start here with M3T3 again. I'm going to just fill them in parallel where they're the same. And the difference is that goes to STA M4T1. Okay. So for the M4 cycle, M4 is for LDA, it's a memory read cycle. So it's going to look kind of like this MOV M2 read cycle. So we start out here with turning on, well, the address. The address we're using is LDA WZ. Hold on. That would keep us from compiling, wouldn't it? Not sure why it didn't. Stray / in program. That's bad. I need to wind it back until I find what broke that. That looks like something got stuffed in from the top of the file. See, this is the problem with not committing to Git the moment I had LDAX and STAX running. So declarations, and then we went down. That's right, I went down to the bottom and copied those declarations in. I must have just put them in just slightly the wrong place. That's fine. So M2T3, charting it out here. Again, LDA, STA, M2T3 puts it in the Z register, which is the low byte. And then the W register is the high byte. So this, we're going to form the address WZ. So M4T1. So W is on the top, C is on the bottom. Toss it into IDAL, toss IDAL into adder, and this is a memory read because it's an LDA. We do need to have a T-wait for the LDA. Let's fix that up. Okay, M4T1, set IDAL, set adder, set data, raise sync. Next state is M4T2. M4T2 needs to drop sync, tri-state data, and raise data bus in. And it needs to potentially have a wait state. There's TW. TW will be forcing a re-raise on dbin, and will decide again if it wants to do a wait state. LDA T3. This is the final cycle, so there's that, and then we raise, lower weight. Now LDA will always set the A register from data. So there's LDA. So now we pick up the STA sequence. So here's where we're writing memory for that. So STA M3T3 is going to be like the LDA M3T3. What is going on with OBS? It just claimed to have disconnected from the stream and reconnected. Well, the stream appears to be going. Okay, well, we've recovered. So WZ is the address. This is an STA, so it's an M-write cycle. And we get into M4T3, where we finish up that cycle, just like that. So that should have LDA and STA done. Used but never defined. Oh, right, because it's LDA and STA are separate. And here. So one big difference that I can't avoid from the techniques I used in the 90s to today is that the compiler warnings are much, much better now. And I would not give that up for the world. So we have LDA, STA supposedly hooked up, supposedly connected, and supposedly working. Let's test it. ASM load store test. LDA, A data, CPI 77 hex, JZ $+4, DB08H, subtest failed. STA, A data. What I want to do is put out a plot of each of these after the store back. And we do not need to do a next subtest. Well, if we do that, I don't think we get a runt plot at the end. We might. And nop halt at the end, just to make sure that we actually have a defined way of trailing things out. Now, here in our test I8080 LDST test, we now want to also test like that. Test condition failed. So STA is not actually sending its data back. So to see what's going on, we're going to need to look at our plots, but it's specifically STA. So before I do source load store. So what is happening with STA? So STA gets in here at 2 bops, and then at M2T3, it's going to go to state LDA STA M2T3, which is shared code. I think I'm going to unshare that. Since it's the only function that's shared between the two. Okay, so we get to STA M2T3 in the T3 part. So we are loading the first byte of the address, which should be the low byte, into Z. T3 M3 we're getting here. We load the high byte into W. Then we get into T4 M1, which we completely failed to fill in. This is why we test. So M4 T1, we assert sync. See, I was off by 1. M4 T2, we drop sync like that. Drop sync, tri-state data, and then at M4 T3, we hit the right signal. And this is not D-try, it's D-set data val A. So literally, we were just writing garbage because we were strobing WR, but MWrite wasn't turned on, so did we write anything? We definitely exercised some undefined behaviors there. There we go. Did it without breaking out the plot. Let's take a look at the plots. Delete them to be sure that they are fresh. Okay. So load store 1. This is LDST BIST 1, which is doing an LDAX through BC and then an STAX. And there's our memory write. And there's through DE. There's the memory write. And we can check the data is 22 and the address is 81. And here's LDA and STA. Did I do those? Yeah, WZ. So B20082 is the address. Somebody is putting a 21 in the Z register. Why would we be getting a 21 in the Z register? So 3A. So that's the LDA. So CPU address there. LDA, compare immediate with 77. So here's our 77 accumulator temp register, ACT temp. Then we have the CA. Ah, right. The 21 is the low byte of the jump address. So we have to load that in WZ. And we should see the PC skip forward. It is 20 briefly, it's 21 briefly, but it goes to 22 before we do another fetch. So the address fetches DEF2122. So 1F is that 0 byte, and we go right to 21 and 22. So then we do our STA. 8200 comes back into WNZ. And here's our write pulse here. Data is 77, address is 82. That is correct. And so we have confirmed that not only are we passing the test, but the diagram looks right. And then we have a LDST4, which is blank, because I think, what? Why did we have that? Probably because there is a trace file. One, two, three. Yeah, there's a trace file down here that is stale. Do that. I am going to modify something to be sure that we run again. We regenerate the PNGs. And there we have it, LDST 1, 2, and 3. Okay, so that finishes up the LDA and STA instructions. So far, so good. What is next on the docket? Oh, next on the docket is sending this to Git so that I don't wipe it out like I almost did. Git Kraken. So, stage all files. The comment here is add LDAX, STAX, LDA, STA. So there's the test. So also fix decoding that's fixed. Oh, I-8080 org needs to include the new figures. SHLD and LHLD are not done yet. Oh, LHLD and SHLD are just like LDAX and STAX, but they're for HL. Ha ha. Let's finish those. This is really, I'm gonna pretend there's something called LDAX HL, and we'll just use the right opcode for it. Make sure I'm doing the right thing here. No, that is incorrect. That is incorrect. LHLD does not do the equivalent of LDAX. That would be the MOV. So we are going to undo what we just did here. This does mean that I have not yet implemented LHLD and SHLD, which are a 16-bit, so they have 2 bytes of immediate followed by 2. So LHLD and SHLD are much like LDA, STA, except they move 2 bytes afterwards. There we go. That's updated. So now if I fontify and bring in line, we should now see these, but we don't because I got the name wrong. So BIST plot, LDST BIST plot 3 has the right stuff now, 7.7, LDA, STA. It now has this and this for LDAX, STAX. There we go. Now back to committing. So notice I fixed that there. These guys are now implemented. XTHL, I've now got some stuff down at the bottom of the file. There should be a blank line there. There. Okay, hex file. The impl adds it. Test adds it. We did this as part of our cleanup. I hadn't committed it yet, but basically I am saying route all the undefined instructions to NOP so they don't count. When we up here, you'll see that we have a counter for unimplemented instruction codes, and that no longer will include the undefined codes. That's fixed. This is newly implemented. LXI, we fixed the location of a backslash. That's great. Support, we do not want to commit that, unstage that hunk, and discard that hunk. And that should have triggered a build. It did, and we check the results, and we are still passing. So, ASM test. Route these through assert EQ so that I can disable the actual abort. Would store test. Here we go. I guess I can remove the rest of that. Move the thing B off to the side here. I'm going to leave these comments in because they are actually useful. Another good thing about moving things into Git is I actually look at the changes that I've made so far, and I can decide whether they are up to snuff or not. Commit changes. I'm going to go ahead and push this. I like to push things out to GitHub. It's the equivalent of making an offsite backup. And now we can turn off Git Kraken here and here. So I am actually having trouble accessing GitHub right now. There we go. Took it about 30 seconds before it came back with an acknowledge that I pushed to it. Next instruction. Well, the next on my official list is LHLD and SHLD. So these are like LDA, STA, but they move more data. That's fine. Okay. They're going to start out much the same. Difference is going to be once we have the address, we don't just have an M4, we also have an M5. Same thing with here. Like that. And what I am going to do is I'm going to take this entire section of code that does LDA. Oh. Careful. Like that. And we're going to go back down to LDA underscore. So from here on down, we've now duplicated it. So now if I ran these instructions, they would do the same thing as STA instead of SHLD. And I wouldn't be defining all of them because there's some missing. So we have these static declarations for M5. Why didn't it tell me that they were being declared but not defined? There we go. I guess I just didn't wait long enough for my build to finish. So these are all the M5s. So LHLD, very, very similar right up until when I say val of A. Nope, when I say D set of A. LHLD is going to load the low byte and then the high byte. So M4, T3. So I need to duplicate M4 into an M5. This guy no longer raises M1 int. Instead, it sets CPU next to M5 T1. Now, M5 is going to be doing that again, but it needs to have incremented WZ. Let us check the PDF to see when and where that is supposed to happen. So LDAX and STAX. Nope, LHLD, SHLD. So here in M4T2, WZ equals WZ plus 1. M4T2, got it. So I'm actually storing WZ as a pair of bytes. I'm not storing a WZ register, so I can't just increment it and store it. What I need to do is okay, that will mask it properly. That will shift it and mask it properly. But I'm doing that during M4T wait. It needs to be here. So now WZ has the appropriate thing. So when we load it up, it'll be the IDAL incremented. Now, the other thing I could do is simply store that back to IDAL, not worry about updating WZ. But the PDF is clear that it is incrementing WZ and then using WZ as the output. So let's keep this matching. Now, M5, we do the normal data in dance. And now we're loading HL. We're going to be loading the second byte into H. There we go. And that ends the LHLD. Now, SHLD, we need to do something very similar. So, edits we made. Well, first of all, M4 needs to be duplicated into M5. And we no longer raise here. Instead, we set this here, M5T1. So M4T2 needs to increment WZ here. M5T1 will reassert as the address with the new data. And here where we are storing in M5, we want to store the high byte of H, and in M4 where we are storing it's the low byte. So L and then H. So that should set up LHLD and SHLD properly. It compiles without warnings. Let's look at our test code. HLD. We need to do some compares in there. So HL data, I'm going to do 55 hex and 66 hex. So 55 should land in L and 66 should land in the H. Actually, let's do a DW. 1, 2, 3, 4 hex. Should be 3, 4 followed by 1, 2 in the listing file. Yep, that's correct. Okay, so this is now telling us that we have an unimplemented instruction that we are encountering. Well, that's because I didn't set it up. That's better. So as a null, fail, hit at PC, whatever. Well, that's a bad message. So I'm sending in a null for the plot name. Oh, that's in post. So in post, we don't have a plot name. So if we don't have a plot name, I won't print it. That also means that we need to assure that inside post we do set plot name to null. Actually, let's do it even better. Instead of plot name, I'm going to use the hex file name. Because we do always have that. So this says we're getting a fail hit at PC 35 hex. Well, 35 is this guy right here, which means the L register is not getting a 3-4. So that's a bug, and we can fix that. Let's get a plot so we can see what's going on cleanly. Okay, so here it is. So starting at 25 hex, we have our ALHLD, 252627. H gets 12. L is not being loaded. Pretty clear. Hold on. You know, LHLD sets WZ. What am I thinking? So LHLD comes in here. We should get something reading from 83 hex here. So we load Z, we load W. Which we send to the address register. LHLD, wait. And hey, there it is. It's setting it into A, so the M4 cycle should be loading it into the L register. And that is our bug. So just reading it carefully as I burst this in, I can get rid of those. I know what this was. I should have seen that. I think I am plotting too wide here, so I'm not focusing in on just the instruction that's got the problem. Test condition failed. So I think this is because I am not comparing the new HL data that I'm storing. And that is true. Did that not run? Oh, her to her, 1, 2. There we go. Helps if I get the test code written properly. And now we have LHLD and SHLD working. I am going to commit that. But first, doc. LHLD and SHLD are now implemented. Let's make sure that I have the latest and greatest PNG versions of those. So this does an LHLD and an SHLD. Entirely too busy. Can't see what's on the data and address buses because it's too busy. But we do see SHLD is happening over here. Boom, boom. Memread and memwrite, we are seeing all sorts of stuff happening. We see some wait states here that aren't happening. I'm not asserting wait. Dub, dub, dub. Bonk, bonk. Let's check and make sure I have asserting wait at the right time. Source. So M4 T2 or TW. These guys in the wait state are not asserting wait. We are lowering it, but M5 TW there we go. So now we're seeing our wait pulses come through. All the time we're reading from ROM, I expect to see those wait pulses. And it should line up with the second half of the memr, like that. With the writes here, that's good. Notice that the Z is getting incremented, so A3, A4, that's good. If we could read data, we would see the correct data here. Yeah. So I think the other thing I want to do is in the test file, I am going to say next subtest before the SHLD. And this should now have a 5. There we go. That's nice and wide. So I am also going to do a next subtest. So we will see just a plot of HL, followed by a boring plot with the compares, followed by a plot of the store. So 4 is the SHLD, 25, 26, 27, 83, 84, 28. So 25, here's our immediates coming in, here's our store going out, and there's the fetch of the next instruction. 6 is a whole bunch of compares and branches. And, oops, no, 6 is the, 5 is the compares and branches. That's what I expected to see. And 6 is the store. So we see opcode, operand, store, and the opcode that says end of plot. So to make these nicer, I'm going to insert a NOP before it. There we go. So NOP and opcode, immediate, load, next instruction. And IR, this is the NOP coming in, followed by the load, immediate, or store is SHLD. I really should have a way of decoding the instruction register. SHLD, immediate, data, next instruction. There's our writes. So there's the LHLD. There's comparing the HL values, so we see that the address 25, 26, 27, 28, 83, 84, 29. Whoops, what? Wait. Yeah, helps if I don't. 5, 6. Yeah, even as I was saying that, that was just not right. So SHLD alone, check HL values, LHLD alone. So LHLD, 25, 26, 27, 28, 83, 84, 29, no writes. We're doing the loads. This is a whole bunch of moves and compares. So we get A from one of them, and you do compare in a branch to A, B, C, D, E, F, 3, 1. So we skip 3, 0, which would have been an error. 2, 3, 4, 5, 6, 8, 3, 7 had the error byte in it. And then we get to SHLD alone down here. And this is again the SHLD, so NOP and opcode, operands, writes, boom. So this leaves us with calls, returns, restarts, and XTHL to go. I'm going to commit this to GitHub. I'm going to go look over, see if there's places I need to fix up comments or polish up things a little bit, and that's the end of the session. So keep it small, keep it fast.